Good morning, good afternoon, good evening, wherever you are on this planet, and welcome to our SETI Live. Surprise, surprise, I'm not Beth Johnson. She was supposed to be part of the SETI Live, but she's sick, and she has no voice. So she decided that I will be the right person to replace her. And today we are going to talk about Titan. So welcome to all our viewers. Thank you for joining us. And to talk about this amazing Saturnian moon, the largest moon of Saturn, and a place which is very exotic, full of rivers, seas. We're going to talk about that. Pounds of methane and other exotic things. We have with us Dr. Sam Birch. Hi, Sam. How are you?
Hey, nice to be here.
Nice meeting you. You are assistant professor at Brown University. Is that
Yep.
correct? Yeah. That's where you're calling us from?
Yep.
Good, good. All right, so let's start a bit. Context, important. We are talking about Titan. So Titan is a very special moon in our solar system. As I mentioned, it has this very interesting surface. We know that thanks to the Cassini mission. He has a very thick atmosphere. He has liquid on the surface. So Sam, you tell us a bit why you are interested in studying this very special place in our solar system.
I think you hinted at it there. Titan is, I think, the only other place other than Earth that has something to offer everyone as a scientist, and even the public. It's the only place where it's raining right now. It's raining liquid methane. It has rivers flowing with that methane down to the coasts. Wind is blowing and kicking up waves on those seas. It's got a global desert across the entire equator. It's got mountains, this thick atmosphere that's raining plastics down to the surface, and this whole global subsurface water ocean that may or may not be in contact with this organic rich surface. So kind of has something for everyone. And it's a really, really exciting place where everything looks similar, but behaves very, very differently. So it's a playground kind of for us as well.
Yeah, it's a playground for geomorphologists, geologists like you. So you mentioned that Titan has those interesting fluvial structures like rivers, yet seas, and so on. So the point of your paper is basically that it doesn't have something we were expecting to see, which are river deltas.
Yep. Yeah. So we kind of noticed it a while ago when I first was looking at Titan as an undergraduate student. And you see these huge rivers that are like the size of the Mississippi in their width, or bigger, right? They're multiple kilometers or miles across. If you're standing on the edge, you wouldn't be able to see the other side of the river, right? Those size rivers on Earth, when they hit the coasts of Earth's oceans, always have a river delta. And when we looked at the ones on Titan, only one of them out of like 70 something of that size had a river delta. So it seems to be the exact opposite. And the point of the paper was, is this real, or was Cassini just not able to see the deltas? And in the paper, we kind of go through this hypothesis carefully, and we're like, actually, the deltas really aren't there, which as a geomorphologist is kind of disappointing, right? You want to see this feature and study its shape and what you can learn about the climate. So we kind of have to do the opposite of, they should be there, but now they're not. And so the question next is why? Why is that?
Okay, so before we answer to why, let me say hi to people who are watching us from this planet Earth. We have people from Sweden, Salve, from Oregon. Welcome. We are talking about Titan, an exotic satellite of Saturn. And the mystery here is that recent analysis show that despite having rivers, Titan doesn't have any delta. So how did you figure this out? What did you use as an instrument? Because I do remember, I'm going to confess something. We observed Titan with the Keck telescope and the adaptive optic system for years. And frankly, when you look at specific wavelengths in visible and infrared, most of the time you don't see anything because Titan has such a thick atmosphere that you don't see the surface. So how did you manage to get observation of the surface and see whether or not there was delta?
So we used data from the Cassini mission. It had a radar. The instrument was called the Titan Radar Mapper. and it was designed specifically to look and map Titan's surface, hence the name. And so out in the radio wavelengths, 2 centimeters is the wavelength. The atmosphere is completely transparent, and the radar can see right through it, just like Earth, right? That's how we send radio waves out to space. And so we use that data. The first thing that we wanted to do is like, if you have, when you look at radar pictures of Earth, water is very absorptive, so it appears very black in the images. We use it a lot to look for like flooding and stuff after storms, because you can see through the clouds and you can see the water on the surface to like then direct resources for people. On Titan, the methane is super transparent. And so you can see through 100 meters, kind of no problem. You can see right to the seafloor. So if you're trying to map a coastal landscape, you don't get that bright land, dark sea contrast that you get on Earth. And so we tested it on Earth. Like, could we still see the Mississippi River Delta? Could we still see like South Padre Island of Texas? Big features. And are they even visible? And kind of what was Cassini sensitive to? And then we went back to Titan and re-looked at the Cassini data. Once we kind of figured out what Cassini should and should not see. And the takeaway was it should see the big things, and especially if they extend into deeper liquids. And then when we went to Titan, and we still saw almost nothing. And so it was like, okay, yep, they're really not there. So
it's always difficult to publish a paper on negative discoveries, basically. Even though they're extremely important, if you don't see what you expect to see, you probably spend a lot of your time trying to make sure that there was not an issue with the instrument or an issue with the lack of sensitivity or things like that. So that's why you made a comparison with Earth, I'm assuming. Is that correct?
Yeah. So we know Earth really well. We know what its landforms look like. We know the processes that are shaping them. No, compared to Titan, we know things really well. And so we know the delta's there, right? And so if we simulate what it would look like to Cassini, and if we can't see it, and then we did that for tons and tons of landscapes all across the coastal US. And we kind of trained ourselves and showed quantitatively, if like you can't see this, you can't see this, you'd probably miss that one, or you'd probably misinterpret that one. But the big stuff you'd still see was kind of the takeaway.
All right. So what does that tell us about Titan and how it works? What can we learn about the erosion? I mean, delta are formed by erosion, by the type of sediment and stuff like that, right? It's very complex.
So deltas are basically, you take all the sediment eroded and transported off the continents, and when it hits the ocean, you concentrate it into a wedge, a triangle, right? A delta shape, like the Greek letter. And so they're kind of like this, you stuff everything into one tiny spot, and so what it means on Titan, we're still kind of working that one out. It could mean that it doesn't have transportable sediment. So it could have these rivers flowing and they could be completely empty of sediment, which would be a mystery of why that would be. It's unlikely because we see the river, or we see the dunes all across Titan, right? That's sediment. The one spot we landed on Titan with the Huygens probe, we saw a bunch of river gravel just sitting there. So if I happened to land anywhere on Earth and I saw that, like it's a decent assumption that there's some sediment on the landscape that can move. We showed in a separate paper a couple years ago now that sediment is, if it's produced, should reach the coasts because it's more mobile than sediment on Earth relatively. And so that was our first hypothesis, is like, hey, maybe the rivers aren't good at transporting sediment. And the answer was, no, it's the opposite. They're actually better than Earth. And then the next one was, hey, maybe we can't see them. And that was like, no, we actually can see them. So there's some students up at MIT that we're working with that are working on other hypotheses that are like, maybe wind and waves can move the sediment and you kind of smear it away. That would be one. And that happens on Earth all the time. So if you look at the river, right at the Texas-Mexico border, there's a little river delta and a big barrier island coming off to the north of it. that is a river delta. It just doesn't look like the Mississippi one. So they don't all look the same. And that's because waves and tides can move stuff around once it's there. So that's one hypothesis. Maybe we'll see. Another hypothesis is if you have the sea level going up and down quickly on Titan, like it does on Earth, you're also going to smear where you put that sediment. So maybe you're just disguising it that way. And then the last hypothesis that's more exotic that we're working on is maybe the rivers, when they hit the seas, they just go straight down. And rivers on Earth are buoyant. So if you go to like the end of a river and you see this big plume of stuff coming out, it's because the river is slowing down and it's dumping out all of its sediment. And that's because fresh water is more buoyant than salty water. On Titan, it might be the opposite. And so your river hits the sea and just is like, I don't care that I just hit the sea. I'm going to keep going and do my own thing. So maybe that's kind of where we're at. And we're testing all those with like models, some math, some lab experiments. And so we'll see.
Good. So
there's something else that we haven't thought of yet. Probably.
There is probably some other hypotheses that maybe our viewers will come out with some ideas here. By the way, if you have any questions, we're going to take a few questions for our speaker. Okay, so you don't have a clear explanation. You have multiple ideas. What can you say? We are the SETI Institute, and we always love thinking about the research done by our colleagues as kind of a way to detect life or to explain life. I mean, we're focusing on life, astrobiology in general. So what your research can tell us about habitability or sign of life on Titan specifically?
I think there's 3 answers to that. I'll give them quick here. One, Titan's surface is really, really cold and it doesn't have liquid water. So life in liquid methane would be hard. There is some like theory that it might be possible-ish. So it's going to be difficult at Titan surface. It doesn't mean it's impossible. And if there's ever a place that it would be along shorelines where you got a lot of evaporation precipitation, which creates what are called chemical potentials that life likes to take advantage of. And so on Earth, deltas are full of life. And it's kind of where you mix different fluids, lots of fun stuff and fun chemistry can happen. So if there is a spot on Titan's surface, it would be there. Still unlikely. The bigger thing is, I think we can better understand how rivers and deltas, or deltas and then rivers and coasts interact kind of quantitatively for understanding preservation of stuff. So Mars has lots of deltas. So if we can fundamentally understand how deltas work by going to something totally different, then we can learn something more about these habitable environments on Mars. And then on Earth, right? I mean, a huge chunk of Earth's population lives on river deltas, and these are prone to flooding and with rising sea levels, right? These are the first things that are going to be most vulnerable. And Titan is a place where we can understand the true fundamentals of how these things are working. And that's kind of what's exciting to me. It's like kind of the habitability of our own planet, of us, if that makes sense. It's not so much looking for life on other planets. If you are going to do it on Titan, you got to go to the subsurface.
No. There is delta as well on Mars, no?
Yeah, so most missions we sent to Mars have gone to what they thought were lakes, or things that might have been lakes that maybe weren't in the end, and stuff that had river deltas and sediments. Gale Crater has deltas around it. That's where the Curiosity rover is. Jezero Crater is where the Perseverance rover is. That had a delta. That's why we went there. Deltas are really good at preserving stuff because you got all this sediment raining out, kind of just keep stuff there, and then you lock it in through time, right? And so that lets you then go read it kind of like a book. And so deltas are really exciting for that sense. On top of their whole freshwater, saltwater mixing stuff.
All right, so I noticed that you're wearing a t-shirt. Can you show us the t-shirt you're wearing?
Oh, yeah.
Dragonfly. Nice. So this is not a science fiction movie for people who don't follow. Dragonfly is the next mission in for Titan, right? Can you tell us a bit about Dragonfly and your involvement in the mission? You're not
So
only wearing the T-shirt, I'm assuming.
Dragonfly, I think, is the most exciting thing NASA has done since Apollo, maybe. Um, it's a 1-ton octocopter that's powered by a nuclear reactor, and it's got all these instruments on the inside, ovens and stuff to see what Titan's made out of. And it's going to go fly around on Titan. So imagine the Curiosity or Perseverance rovers, except it's flying. That's Dragonfly. And it's going to go to Titan, where the wind is blowing, dunes are moving, maybe it rains. It's going to be absolutely spectacular. And we're not going to fly once or twice. We're just going to fly once a month, and we're going to keep doing it. So
it's going to hop in different area of Titan and do some experiment on the surface and go to other places.
Yep. So it has drills to ingest material into the. It's got a bunch of mass spectrometers inside of it to see what all this stuff is. It's got a seismometer that it can drop down from its belly. It's got all sorts of wind and humidity sensors and cameras. So yeah, we'll spend time on the surface, and then when we're ready to fly, we'll pick up the whole thing and fly to the next spot.
So the temperature and the pressure on Titan, do you know the numbers on the top of your head?
Yeah, the pressure is 1.5 times the surface pressure on Earth.
Okay.
So it's a bit higher. The density of the atmosphere is 4 times higher, and the gravity is 1/7. So that means, I joke that if you had like Leonardo da Vinci's flying machines, they would have worked on Titan. He was just born on the wrong planet.
Yeah.
If you had big enough wings and you flapped them like I did and I ran, I could like get a little lift. So it's a lot easier to fly on Titan, and that's why we're doing it. And then the temperature in the middle of winter, at the middle of night, it's like 90 Kelvin. And then in the middle of summer at the equator, it's like 94 Kelvin. So it's pretty much the same temperature no matter where you are.
Oh, yeah. So 90 Kelvin in Fahrenheit, because I know people are going to ask.
Minus 290 or something.
Okay.
It's cold, really cold.
Very cold, very cold. Okay, good. So we're gonna take a few questions from people. So we have one from Zap. Oh my god! Every time you ask a question, and every time I have a hard time saying the name. Zapfan. Does the original material melt and therefore disappear?
So the bedrock, the rocks, if you were walking around on Titan and crunching sediment under your boot, is probably water ice. And at 90 Kelvin, it's as hard as rock. So it wouldn't melt. What might be happening, there's 2 sources of sediment. So there's another source from the atmosphere. And if you have these organic sediments raining out, that is what the dunes are made out of, there is some of them in theory that dissolve in liquid methane. So not melt, but dissolve. And that would be one way to not have river deltas. You would just dissolve the landscape. And you do have dissolution landscapes on Earth. And some of those rivers don't have anything at the end because, again, it's just all it's dissolved in the fluid itself. So that would be one way. Yeah. There isn't a lot of dissolved material produced over the age of the solar system. So it would be harder to do. But that is one hypothesis. Yeah.
All right. So there is more questions. So if you have more questions, don't hesitate to ask. We can even talk about Dragonfly. In fact, I have a question for Dragonfly. So did they map already the location, the landing site? So are you still arguing or discussing about this?
No, we are going to. So the mission is mostly chemistry focused, and we're going to the south end of an impact crater called Salt Crater. It's near Titan's equator, very far away from the poles and the active rivers. The plan is to land in the dune field just to the south of the crater. We don't know how hard the surface is or the slopes and all these things. We don't have really good data like we would on Mars, for instance, or the moon to build super precise maps and where all the big rocks are. But the nice thing about dunes is that they're predictable, right? It's just a big pile of sand. You know what the slopes could be. They can't be that steep. And so the plan is to land in between two dunes and kind of start and get our feet wet in that dune field, and then move north towards the crater, because what we want to investigate is places where water and organics might have mixed, and for how long and what chemistry happened. We don't know any of that chemistry, right? And so an impact crater on Titan is great because you would melt all that ice. So you'd have liquid water and organics at the surface in a warm water environment for potentially a while. And you want to kind of see how far chemistry can go. So that's the main goal of the mission, actually, is to investigate that chemistry.
Are you going to land on the delta, or on the only delta, or
the only delta is at Titan South,
Okay.
along a lake, so we'll never get there. No.
No.
We'll go to the crater, and then I don't know how long we can go after that. Yeah, the plan is to just get to like the edge of the crater basically right now. There could be similar sedimentary deposits coming off of the crater, and those are the ones I'm really excited about.
Mm-hmm.
Maybe they're there, maybe they're not. We definitely can't see them. If you look at the data, it's like super noisy, and so maybe there's something there. In theory, there should be. So that's what I'm excited to see.
All right. There is. So, what's the next thing for you? What are you working on? I mean, Dragonfly is landing in what, in 2030?
Oh, don't quote me on that one.
Let me Google it.
9 years from now.
Yeah, something like that. So you have 9 years.
35.
What are you gonna do in the 9 years? The upcoming
Good
9 years.
First, I mean, continue. We've gotten to the point with Cassini where we've kind of figured out what's on Titan's surface and what isn't on deltas. The next step is trying to figure out what's going on, and this is where we're moving into like theory land and modeling and experiments, and also experiments to figure out what are the different rocks like, what are Titan's materials, how do they behave if you stick some of these organics that are produced in the atmosphere and methane, what happens, right? Nobody's done that. And so there's a lot of fundamentals now that we kind of know what's there and are starting to figure out what these things are. How do they behave? Why do they produce things that look the exact same as here on Earth? But once you do this very simple math, you're like, oh no, that's way different. And so we're kind of at that point now where we have to use the data that we have to figure out what's actually happening and come up with new theories that we can test with Dragonfly. Does that kind of answer your question? There's a lot to do.
There's a lot to do. So I check. It's landing. The landing is scheduled in 2034.
Nice.
But the launch is in 2028. Are you going to go to the launch?
Hope so. It'll be fun.
Okay.
I've never seen a launch, so.
I'm not gonna ask you which rocket launching it because I don't know, to be honest.
Oh, I don't know that one either.
But yeah, it's gonna be an amazing mission because it's gonna be basically the first mission we send, which is only. I mean, we have sent an helicopter on Mars, but we never send a mission which is itself flying. I mean, the entire mission is the octo. How you call it again?
Octocopter.
Octocopter. That's the entire mission. It's the size of what? It's 3 meters by 1. I've seen
It's the size of like a minivan.
Yeah.
Basically, it's huge.
Very impressive. And it's probably
We went 0 to 60 here. Like Ingenuity was super tiny. It was like the size of my water bottle. Really tiny. It was a tech demo. Can we fly on other planets? And then we're like, yeah, let's fly a 1-ton minivan.
Far away from us in a super cold environment.
Dusty and not a lot of light. It's going to be amazing. So
that's what NASA does best. I mean, come on. Someone has to do it. It has to be NASA.
Yeah.
Good. All right. Well, thank you very much. Is there anything you want to add about? Oh, where can we have information about your research and read about your work in general?
Yeah, I don't really have any social media. curmudgeon like that.
So we have to read your scientific paper.
No. Yeah, if you, I mean, Google, but geomorph dot. Oh, I don't even know my own website. Google Sam Birch Brown. I'll be there.
Okay, and we will find you.
Yeah, thanks for having me. This was fun.
Thank you very much for coming to tell us a bit about the wonder of Titan and the fact that there is no delta, and you've been looking for them. But it's okay; it's part of science. And
Yep.
I like the fact that we have people who come sometimes to tell us about the fact that they will be looking for something and they did not find it, because
Yep.
that's the way science works. It's not only flashy, amazing result. Sometimes negative result is important result because it shows that we don't have a clear understanding of the system yet, and that's good. There'll be some cool stuff to discover in the future.
Exactly. You said
And,
perfectly.
and you will make them with the Dragonfly mission. All right? Cool.
Thanks so
Well,
much.
thank you. Thank you to all our viewers for watching us. I saw there is some people who join us from Canada and other parts of the world. This is the SETI Live from the SETI Institute. You can support this program by liking our videos, posting comments. We read the comments, and we answer to them as well by telling about the SETI Institute, the SETI Live, and what you learn about. We need your support. Remember, this is a kind of a program that we put together with the hope of having a lot of people watching us, of course. You can also support the SETI Institute itself and this specific program by going to seti.org/give now. Visit our website. You can also enroll to receive our newsletter called Journée, where you hear about all the amazing research we are doing here at the SETI Institute. And yeah, thanks again, Sam. See you in 5 years to talk about the launch of Dragonfly. I hope to be invited as well, by the way. So put me on the guest list. Okay. Thank you again. And see you next week for another. Bye bye.